Okay, good afternoon everybody. I hope we have some viewers. Today is probably Nimanjan in your area. Okay, I hope you are here to watch this particular discussion. Okay, so yesterday we discussed about the syllabus of surveying and which are the important areas for us. I told you GATE is nowadays concentrating a little bit more about the untapped areas from GATE. Okay, so today we have I've listed some questions here. That is mostly about those areas from which GATE has not really asked. Okay, because there is no point in me discussing the same pattern of questions that GATE have asked. Okay, so I hope you will go through the previous year GATE questions and as well as ESE questions. Okay, and we'll try and discuss some questions. See, for ESE, I'll not say there is a specific area, right? For ESE, I've told you that yesterday also. They can ask you questions from everywhere. Okay. What I have done is I've made some questions. I've collected some questions from which GATE has not asked so far. Okay. ESE also have not asked so far. Okay. So you can consider this both as GATE and ESE. The theoretical question will be more towards the ESE prelims point of view. We have some numericals which cannot be solved by using our which can't be solved by not having a calc. So those questions, ESE point of view, are not very important for you. Theoretical questions, yes, for GATE as well as ESE, it is important. Okay, let us begin. Okay, so let us begin with this particular question here. So we'll start with GPS, right? So selective availability, okay, it's an error. Selective availability in GPS is a dash. Selective availability in GPS is a natural error, intentional error, systematic error, bias. The correct answer for this is, we can say, is intentional error. Okay, because you see, when GPS was first, incepted or first came into existence, actually, it was not really made available to all the civilians. It was basically a military technology, right? So they did not want the civilian users to have it. But later on, it was made public. It was made available for the general public in US, right? But at that time, they did not want to give the entire accuracy that GPS can give you. Okay, the entire accuracy, the kind of accuracy the military has, they did not want that civilian people or other people to have. So they made the accuracy a little bit less. Okay. There are actually two communication codes and all. P code is there, course acquisition code, like that is there. P code stands for precision code, where you get higher accuracy. That code was not really made available for the general public. So whatever data that the general users, the general public were getting, that was not really the entire range of data that GPS can provide, or the entire range of accuracy that the GPS can provide. So it was selectively available for the public users, right? So therefore we call it as selective availability. So that's an intentionally made an error in GPS. Okay. Satellite on board, quartz clock, atomic clocks, stopwatch, digital clock. Okay. This is another question from GPS. On board our satellites, what kind of clocking system we use? The answer is atomic clock. Okay. On board GPS satellites, we have atomic clocks. Inside user-based equipments, we have quartz clock. Inside user equipment, we have quartz clock. So you see, the satellites are having atomic clocks. The user equipment are having quartz clock. Who is more accurate? Obviously, atomic clocks are more accurate. It's very, very accurate. Okay. So there is a small problem. Okay. See, if I'm using one set of clocks which is having high accuracy in the satellite, and if I'm using another set of clocks in user equipment which is having less accuracy, there is no compatibility. Okay, there is no compatibility. High accuracy at one point, lower accuracy at another point means there is no compatibility. So there will be an error. Okay, there will be a bias coming. This bias is known as time bias. This bias is known as time bias. So, right, apart from calculating your x coordinate, your y coordinate and z coordinate in 3D global coordinates, x, y and z, rather than these three, one more error actually we need, one more unknown quantity we need to take care of. That is the time bias. So this is another reason why we require minimum 4 satellite connections, minimum 4 satellite connections, so that we have some good accuracy over our position. Because please remember, GPS will tell you your position, velocity and time. Time is also an important parameter here. Okay, so right, if I end up keeping atomic clocks in my user equipment, the entire cost of GPS networking will be too high. So the programmers or the engineers came up with a good idea that we will use some less accurate clocks in the user equipment, and the resulting time bias will try and solve by getting one more distance equation by connecting one more satellite. Apart from X, Y and Z, one more satellite connection we have. So therefore that 4 unknown parameters we can calculate. One additional reason why we need 4 satellites. Okay. So atomic clocks are used in satellites, and user based equipments are going to use quartz clocks, right. The other form of vector format is, this is from GIS, right. Data are represented in 2 formats. First one is vector format, second one is raster format. Now, the raster format is associated with the cell-like appearance, okay, block, right, type appearance is there. We call it as pixelated appearance, right. That is the only way in which raster data can be represented. Now, this pixelated appearance is, associated with less resolution. Resolution basically means the clarity that you get from a particular image. Different forms of resolutions are there, but please understand, basic idea of resolution is how clearly you can understand the image represented. Now, raster fails to give a good resolution, whereas vector gives us a very good resolution, because in vector, we are having the representation of data in a sequential manner or a continuous manner. So rather than dividing the entire area into grids like what a raster does, what vector will do is, it will try and represent points, let us say in a coordinate system where a river will be represented by f of xy, a river will be represented by f of xy, and a point will be represented as x1 comma y1, okay. And if there is an area, we can go with the closed integral, okay. So there are 3 types of formats here: line data, point data, as well as polygon or area data. So all of this are part of our vector format. So line format is there, point format is there, polygon format is there. So therefore the answer should be all of this. Okay. So line data for a river or a stream or a, let us say, a road or a canal. Point data for a fire hydrant, position of a fire hydrant. Okay. Polygon data will be area. For example, I want to represent the catchment area of a river, the forested area of a particular state. We go for the polygon format. Yes. So all of these are part of our vector format. Okay. Yes. Let us look at this. The mean temperature of sun's surface is 6000 Kelvin, and the wavelength of the radiation, lambda stands for wavelength, okay, of its radiation is 0.5 micrometers. What is the mean temperature of the Earth's surface for which wavelength is 10 micrometer according to Wein's displacement law in remote sensing concept? Right. Now let us talk about the Wein's displacement theory. Okay. We will briefly try and discuss that. Okay. So basically what Wein's displacement theory says is wavelength of any radiation is inversely proportional to the temperature of the medium through which it travels. So if your medium is having high temperature, wavelength will be shorter. Shorter wavelength will have. If the temperature is too cold, very less, then we'll have longer wavelength. Wavelength will be longer. Temperature is high, wavelength will be shorter. Length of the waves will be shorter. Now, the product of wavelength, actually there is more to it, but we need not go that far. But the product of wavelength and temperature is always going to be a constant A, where A stands for the Wein's displacement constant. If you look at the question that they have given, they did not really mention, right, what's the Wein's displacement constant. But actually we need not worry about it, because if you are having two mediums at two temperatures of T1 and T2, and if you send a wavelength here, it will be having one wavelength here, and it may have another wavelength here. So lambda 1 is different, lambda 2 is different. So what we can write is this: the product of lambda 1 T1, okay, should be equal to lambda 2 T2 should be equal to A. Right, this is what we can write, and to solve our problem, we just need this concept. Right, the product of wavelength and temperature for a wave in one medium is also equal to the product of wavelength and temperature of the same ray in another medium. We are going to use this concept here. Let us go back to the question. Okay. So what is the first temperature given? T1 is 6000 Kelvin. The first wavelength given is 0.5 micrometer. The second wavelength they are giving is lambda 2. What they are asking you to find is what is the surface temperature. So T2. So what we can write is this: lambda 1 into T1. Okay. So lambda 1 into T1 should be equal to lambda 2 into T2. Okay. So let us look at some of your answers. Do we have any answers here? Good afternoon. Good afternoon. Slightly, no, actually Krishna, right now I cannot drag it to the bottom. It will not be possible. Okay. Yeah, starting words not visible due to logo. Okay, can we do anything about that? So I'm reading the question, Krishna. You please try and fill it up. Okay, right. Yeah. So what we can do is we can write lambda 1 T1 is equal to lambda 2 T2. So okay, what is lambda 1 here? Lambda 1 is 0.5. Don't worry about the unit as of now. Both. Yeah, that was my YouTube. Okay. Yeah, don't worry about the units here because the units are all the same. They will cancel. So lambda 1 into 6000 is equal to lambda 2 is 10 into T2 is what they are asking. So if you look here, what is the value of T2? If you look here, T2 will be 0.5 into 6000, okay, divided by 10. So that will turn out to be what? 300, but what's the unit? The unit is Kelvin, 300 Kelvin. So do we have an answer here? No, because everything is in degree Celsius. So how do we convert from Kelvin to degree Celsius? I need not tell you, I need not teach you. Okay, you know that. So what we basically need to do is from 300, we will reduce, right, roughly 273. So there will be 7, makes it 80. To that I need to add 20. So it becomes 27 degrees Celsius. So do we have an option? Yes. So this is the basic concept of remote sensing. Standing on the surface of the earth, we can find what is the surface temperature of our sun. Standing on the surface of the earth's surface, we can calculate what is the surface temperature of the sun. Just we need to know what wavelength ratios of wavelength. If you know that, and temperature in one medium is known, temperature in the other medium is known. So without being in physical contact with the object, we are trying to get information. This is the basic concept of remote sensing. Yeah. Next step, sorry, the source of energy for passive remote sensing is, see this is a previous year question. It's a previous year question, but I just changed the order in which they asked the question. In 2000, if I'm not wrong, 17 gate, they asked this particular question. The type of remote sensing system that uses sun as a source of radiation is dash. The answer is passive remote sensing system. So if you are using sun as a source of energy, the answer is passive remote sensing system. So the source of energy for passive remote sensing is what? Sun. Do we have any answers? One second. I think it will be a little bit late, no problem. Okay. So if you, we cannot really take sun as a source of radiation because sun just reflects, right? And it is reflected by, again, sun only. Its own source and flashlights with the cameras with flashlights, they're all active remote sensing, right? Please read this. A measure of area or size of the smallest dimension on the Earth's surface over which an independent measurement can be made by the sensor is dash. Okay, so here we are having 4 options: spectral resolution, temporal resolution, radiometric resolution, spatial resolution. What is this question trying to ask you? It is trying to ask you a measure of the area or the size of the smallest dimension on the Earth over which it can make an independent measurement. So is that talking about spectral, temporal or radiometric resolution? The answer is, right, the answer is, one second. Yeah, the answer is nothing but spatial resolution, right? The width, the smallest dimension that can be represented by a particular sensor over which it can take an independent measurement is known as spatial resolution. So you imagine you are having sensor 1, we are having sensor 2. Sensor 1 is having a spatial resolution of 30 meter, which means the basic dimension, the smallest unit, the least count you can consider is 30 meter. So the entire information in 30 meter will be considered as one single information. But if you take the sensor 2, which is having, let us say, 5 meter of spatial resolution, if I'm saying like that, it means that the smallest dimension, the least count, we can say like that, is 5 meter. Alright, so every 5 meter will be considered as one set of information. So if you compare 5 and 30 meter, who is having a better spatial resolution? Sensor 2, 5 meters having a better spatial resolution. Okay, right. So that's the idea. Now what do you mean by this spectral resolution? What do you mean by spectral resolution? Look at our human eyes. See, human eyes are only sensitive to a certain wavelength of radiation, that is 400 to 700 nanometer radiation. This particular wavelength region in the electromagnetic spectrum is what we call it as visible spectrum. Okay, 400 nanometer to 700 nanometer. That is where humans can see things. We call it as the visible spectrum. So if there is no 400 to 700 wavelength regions, or no radiation is there between 400 to 700 nanometer, we will say that I cannot see. Right? For example, there is 800 nanometer radiation in a particular room. That's the only radiation present there. I will say, array, it is a dark room. Similarly, if there is only 300 nanometer, I will say, array, it is a dark room. Right? Some aliens will be there that can see in 300 and 700 nanometer, but we humans cannot see. So I will say my spectral resolution is very bad. It is 1. Because I am only sensitive to one wavelength region, 400 to 700 nanometer. So that is my spectral resolution. Only one wavelength region is there. But if you have a sensor, in your satellite that can collect information from, let us say, 150 nanometer to 300 nanometer. Next, 400 nanometer to 700 nanometer. Next, 800 nanometer to 900 nanometer. So 3 wavelength regions it is able to collect. So spectral resolution will be something like 3. Okay. So that is what we call it as spectral resolution. The number of wavelength regions over which it can take measurement, or the number of wavelength region through which it can collect information, that is known as spectral resolution. What do you mean by temporal resolution? It is the frequency of collecting information. Okay. Right, it's the frequency of collecting information. For example, you imagine I am having a temporal resolution of 1 day. My satellite is having a temporal resolution of 1 day, which means that after collecting information from a single point, it will take the same satellite another 1 day to collect information from the same area. So it is collecting information only once in every 1 day. Right, now, is it good to have a higher temporal resolution or a lower temporal resolution? The answer cannot be said, because that depends upon your application. For example, you are a military personnel. Are you happy with a 1 day temporal resolution? The answer is absolutely not. Because if an enemy is trying to attack you, it will take you 1 day, your sensor, your system takes 1 day to update the position of the enemy. That is not good. By the time he'll put bomb and go. Okay, so that does not work. So I need something like, let us say, 30 seconds of temporal resolution. Right, what do you mean by that? Every 30 seconds, right, the position of the enemy is updated. So now I can take my defensive measures, I can take defensive or offensive measures to counteract that particular attack. Yes or no? So that is what we want in terms of military. But imagine you are trying to measure the amount of deforestation happening in India with a temporal resolution of 30 seconds. It is absolutely blunder, because in 30 seconds you don't see much change in the amount of forested areas. So there you can keep the temporal resolution as maybe a 1 week. So in every 1 week we can measure what the change coming, or even if you want, you can go with 1 day also. Understand? So depending upon the application, the temporal resolution will be made finer or lower. Okay. So it's basically the time interval of data collection. And what do you mean by radiometric resolution? It is the sensitivities or the sensitivity of a sensor to the smallest changes in radiant energy. Right, so if, let us say, some X amount of radiant energy is coming and there is a small change of delta X, and if my sensor is able to detect that, I can simply call it as, right, a better radiometric resolution. So the ability to measure the smallest deviations of the radiant energy, that is what we call it as, radiometric resolutions. Okay, so these are the different types of resolutions that we have in remote sensing. I just wanted to explain that, and we can easily frame a questions around it. Okay, look at this. As per particle theory, again, it's about remote sensing electromagnetic radiation only. Energy of a quantum is dash. First of all, what is a quantum? See, quantum is, the basic particle that makes our electromagnetic radiations. As you might know, when the electromagnetic radiations were first made, when the electromagnetic radiations were first identified, not made actually, were first identified, you see, half of the physics world told that they are traveling as waves, the other half told that they are traveling as particles. The people who believed in that wave behavior came up with wave theory, right? And that wave theory basically says that the wavelength of any electromagnetic radiation is inversely proportional to the frequency of its vibration. This is what the wave theory said. And the people who believed that it travels as particle came up with particle theory, where the most elemental particle of an electromagnetic radiation is known as a quanta. It's known as a quanta. And the energy possessed by this particular particle is known as quantum energy. So they came up with a theory known as the quantum theory, and as per this quantum theory, they were able to say the quantum energy possessed by any particle is directly proportional to the frequency of its vibration, which is absolutely very true, right? Even you can say that I give you a particle that is vibrating with high frequency. You take a bee that is flapping its wings very, very fast. The energy of the bee is very, very high. But if you take a same another bee, right, but it is not flapping its wings very fast, with a low speed it is flapping, I'll say it is having less energy. So the frequency of vibration is more energy is there. Frequency of vibration is less energy is there. But they equated it as quantum energy is equal to Planck's constant times frequency. Yes. So this is what quantum theory says. Let us go back to the question. As per particle theory or quantum theory, the energy, quantum energy process is directly proportional to wavelength, inversely proportional to wavelength, square root of wavelength, inversely proportional to square root of wavelength. So even though the theory says that, right, quantum energy is directly proportional to frequency, they are not really asking about frequency. They are asking about wavelength. So tell me what is the relation? Quantum energy is directly proportional to frequency. Frequency and wavelength are inversely related. So what is the conclusion? Quantum energy is inversely proportional to wavelength of the radiation, which is actually true for option B. So you see, first set of people believed in wave theory, second set of people believed in particle theory. We have used both of them to come to this particular conclusion. So finally, what behavior does these electromagnetic radiations have? It has dual nature. Both behavior is there. Wave behavior is there as well as particle behavior is there. Yes, so that's the point I would like to discuss there. Next step. The number of spectral bands used for collecting data in LIS-3 sensor on board IRS-P6 satellite is dash. On board IRS-P6 satellite is dash. Now, I framed this particular question because in 2017 GATE, there was a question on, NASA Landsat program. I told you this particular information in the last class. Okay, they asked about the spectral bands used in enhanced thematic mapper plus ETM plus sensor that is used in NASA Landsat 7 satellite series, right, which is presently inactive or presently decommissioned. But at that time, when they framed the question, it was active. So now I'm asking about LIS-3. What does LIS stands for? Linear Imaging Self-Scanning System, 3rd generation. Okay, and it is used in IRS-P6, which is known as OceanSat. How many spectral bands it is having? So let us just talk about the different sensors used in the IRS satellite program. So we have LIS-1, 1st generation, Linear Imaging Self-Scanning System 1, followed by LIS-2, LIS-3, as well as the latest one is LIS-4. Apart from this, we have the wide field sensor and the advanced wide field sensor as well. These are the different sensors that we have in our Landsat program. Let us look at the spectral bands of this. These are the spectral bands. Okay, so LIS-1 and LIS-2 is having 1, 2, 3, 4 bands. And this region, 0.45 to 0.52, that is the wavelength in micrometer. Do you want to study it? Absolutely not. Don't waste your time studying this. But remember the number. How many are there? There are 4. Okay. There are 4 bands here. LIS-3 again 4. LIS-1, 2 and 3 are having 4. But LIS-4 is having 3. So ulta relation is there. 1, 2, 3 have 4. But LIS-4 is having only 1, 2, 3. 3 sensors. Wide field sensor is having 2, advanced wide field sensor is having 4. They are asking us about the question 3 for that, LIS-3, for that question the answer is 4. So if you go back to this question, right, the answer should be 4. They asked about Landsat, maybe they can ask about IRS also. So just for say insurance policy, I have discussed about this. Yes. Okay, right. So don't worry too much about the wavelength region, just remember the wavelength bands. I hope that makes sense. Okay. That's it. Yeah, now look at this question from photogrammetry. Yeah, please do try and give an answers, okay? Yeah. Yeah, Bukya Naveen, very good. So getting involved, I appreciate that. Yes. Look at this. A relief displacement on an air photograph or an aerial photograph decreases with the increase in flying height, a decrease in distance from the principal point, both B and C. So the basic fundamental equation for relief displacement I can write like this: D is equal to R into H by capital H. Okay. So what is this particular capital H? Capital H is the flying height, the height at which the aircraft is flying. small h is either the height of the object above the ground or the elevation of the object above the datum. If it is ground, you call it as height. If it is datum, you call it as elevation. Okay, so that is h. What is r? R is the radial distance from the principal point of the photograph, this particular parameter, right? Now, how do you get the principal point? Please remember, whenever we take an aerial photograph, we make sure that every photograph is having a minimum 4 marks like this. Or in the corners also we'll provide, which will add up to about 8 marks. So minimum 4 marks are provided. We call them as the fiducial marks, right? So if you join these particular fiducial marks, you'll get the center of the photograph, which is what we will call it as the principal point of the photograph. And if there is a tower here like this, the radial distance is measured from this particular tower to this particular image of the tower to this particular point. That is what we call it as R. Yes. So what they are saying is, what happens to relief displacement with the flying height? So tell me, as the flying height increases, relief displacement should decrease. So decreases with what? Increase in flying height. Decrease in flying height is wrong. Increasing in flying height is correct. Next step, it decreases with the decrease in the radial distance from the principal point. So they are saying that as R value decreases, relief displacement also decreases. Is that true? That is also true. So B and C are correct. So we can go with both B and C. This can again come as a multiple choice question for you. Sorry, multiple select question for you, where the D statement can be wrong. You have to select both B and C. So right now it is multiple choice, right? But it can also come as a multiple select question for you, right? So fundamental understanding of the equations are important. Yes. The product of the distance of plumb point and its horizon point of a vertical photograph from its principal point is focal length square, 2 times focal length square, 3 times focal length square, focal length. So this is more towards the IES part. This is one question from IES. It's not really important for GATE. Okay. I'd like to discuss about our tilted photograph here. Okay. So plumb point and horizon point. Right. So this particular plumb point and horizon point discussion will come only in the case of this tilted photograph here. So you can see our tilted photograph, which is slightly rotated also. So this particular point is known as your horizon point. Okay. From the horizon point, if I drop a vertical, the point where it touches the vertical photograph is what we call it as another point, which is nothing but the plumb point that they are mentioning in the question. So this is what we call it as the plumb line. This is our plumb line. Okay. The plumb line meets my photograph at this point N, which is known as Nather. Right. O is the perspective center of the camera. K, as I just told you, is the principal point of the camera. The distance between O and K is what we call it as the focal length of the camera, F. Right. So the angle between this plumb line and this particular line, OK, that's the camera axis. This is what we call it as the camera axis, is what we call it as the tilt angle. Okay. Tilt angle. Now here you can see on point I. How do you get the point I? If you draw the tilt angle bisector, so this is the entire angle tilt, you draw the bisector of the tilt angle, it will meet my tilted photograph at the point isocenter. We don't want that for this particular question, right? So please understand, this is I. So this N, this I, this K, if I draw with a straight line, if I join them by using a straight line, the resulting line is known as the principal line. This particular line is what we call it as a principal line. If I extend this principal line, right, and from this perspective center, if I drop a horizontal, this horizontal from the perspective center and this principal line will meet at a point here H. What do you call that point as? That is known as the horizon point. That is known as the horizon point. Okay, please understand. The horizontal from the perspective center will meet the extension of the principal line at the horizon point. This and all we have discussed in our ESE point of view. GATE students need not worry about this. Okay. So going back to our question, what they are saying is, what is the product of the distance of plumb point, that's another point here, N, and the horizon point, say H, horizon point of a vertical photograph from its principal point. So the product of, right, N and K, principal point K, and H and K, that means the distance of another point from the principal point, that is NK, multiplied by the distance of horizon point from principal point K. What is the product of this? This is what they are asking. Okay, let us go back to the figure. Yeah, let us go back to the figure. So they are asking you for the product of NK and KH. Okay, so let us look at this figure here. So this is my camera axis, right, and this is a line on the photograph. Now please remember, this angle is always 90 degree, obviously. So this is my photograph, this is my camera axis. Camera axis is always perpendicular to that particular photograph. There is no confusion in that. So this angle is 90 degree. Basically we are getting a right angle triangle here. Tell me, what is tan t degree from this? What is tan t degree from this triangle? Tan t degree is opposite side NK by adjacent side F. Opposite side is what? NK. Adjacent side is what? F. So from this, what is the value of NK? NK is equal to F times tan t degree. It's equal to F times tan t degree. Right, now we need the value of KH. Right, so again this is a right angle triangle. Obviously this is also a right angle triangle here. This entire angle is 90 degree. This is the vertical dropped from O, perspective center O. This is the horizontal dropped from perspective center O. So this entire angle should be 90 degree. Out of which this is t degree. So what is this remaining angle here? This much remaining angle is what we call it as 90 minus t degree. So this is 90 minus t. This angle is 90. Then what should be this angle? This angle is also equal to t degree. That angle is also equal to t degree. Now tell me what is tan t degree here. Let us again take what is tan t degree here. So tan t degree is again opposite side, that is OK, which is nothing but F. Okay, opposite side is OK, which is nothing but F. By adjacent side, that is nothing but HK. Nothing but HK. So what is the value of HK from this? HK is equal to F divided by tan t degree. Okay, F divided by tan degree. So we got the value of NK, we got the value of HK, we just need to multiply them. So NK into HK. So NK into HK. NK is what? Please observe. NK is F tan t degree. So F tan t degree into, what is HK? F by tan t degree. So if you multiply that, you get the answer as F square. You get the answer as F square, which is nothing but option A. Okay, so it's a good question. Okay, so truly speaking, this is a previous year question from Karnataka PSC. In Karnataka PSC, in one of their examinations, they do have field astronomy as part of their syllabus. So they framed this particular question, which is very, very good. Actually, you can find this as one sentence information, like notes we can write. The product of NK and HK in any vertical tilted photograph is always equal to F square. Like that you can study, but this is the proof. Okay, it's a good question they have framed. So some good understanding of your tilted photograph should be there. You should know what is tan theta. That's it. Okay. Right. So yeah, this is a GATE previous year question. So one of my favorite questions in GATE. Okay, how beautifully this question is framed. Let us see. So here it's they're talking about photograph. They are asking about relief displacement. This is what I told you. In GATE syllabus, when it comes to photogrammetry, they have only mentioned about scale and flying height. But they ask you some good questions from relief displacements. Yes. So observe here. Two towers A and B standing vertically on a horizontal ground. So the entire ground is horizontal. Very important point that is. Right. Vertically on a horizontal ground. This is very important point. Okay. Horizontal ground appears in a vertical aerial photograph as shown in figure. So that is my tower A and that's tower B. The length of the image of tower A on the photograph is 1.5 centimeter. The length of the image of the tower A is 1.5 centimeters. Right. Can anybody please tell me what does this 1.5 centimeter mean? What does this 1.5 centimeter mean? Anybody please tell me. Anybody can you tell me? What is that 1.5 centimeters? Okay, anybody? No, Akhil Das. It's not R actually. So this particular point, that is the principal point P there. So it's not really radial distance r. Can you please think about that once more, Akhil? One reply is there from Akhil. See, what is r? I told you, it's a radial distance from the principal point P. But what is P? It's the length of the image of the tower. What is that? See, that is what you call it as your relief displacement. That is exactly what we call it as relief displacement. So, right, the length of this tower on this particular photograph, that is the relief displacement of the tower, the height of the tower that you see in the photograph. Okay, right. And the tower B is 2 centimeter. That means the length of this particular tower is what? 2 centimeter on the photograph. So basically they are saying that the relief displacement for the tower A is 1.5 centimeter and the relief displacement for tower B is what? Is 2 centimeter. Relief displacement for the tower B is 2 centimeter. Now read the question. The distance of the top of the tower A as shown by the arrowhead. So this arrowhead is representing the top of the tower. Okay, this arrowhead, right, is representing what? The top of the tower. They are saying that the distance of the top of the tower A is 4 centimeter and distance of the top of the tower B is 6 centimeter as measured from the principal point P of the photograph. So this point here, we represent it as K, principal point K, but they are representing it as what? P. From this particular point to the top of the tower B, the distance is 6 centimeter. From here to the top of the tower A is what? 4 centimeter. What is that? That is what our Akhil just told us as R. That distance is what we call it as the radial distance. Okay. Okay. So that is the radial distance. Since they are talking about tower, it should be case 2. Okay. So we'll write it as R2. Radial distance to the top of the tower. They are mentioning about a tower. So, they have to come to our case 2 only. So R2 of the tower A is what? 4 centimeters. The radial distance to the top of the tower B is equal to 6 centimeters. Okay, that's it. Now they are saying that the distance, they measured from the principal point of the photograph. If the height of tower B is 80 meter, so the height of the tower B, which is H2 of tower B, is equal to how much? 80 meters. What is the question? The height in meters of the tower A is dash. H2 of A is equal to dash. Right, this is the question. Now let me write down the fundamental equation here. In this particular case, where they are mentioning about the height of the tower, relief displacement D is calculated as R2 H2 divided by H minus H1. So what is D, relief displacement? R2 is the radial distance towards the top of tower, either A or B. H2 is the height of the tower. Capital H is the flying height. H1 is the ground elevation. So if you look at this questions, right, they are giving you D value, they are giving you R2 value, they are almost giving you the H2 value for one tower. But what about the flying height and ground elevation? Right, what about the flying height and ground elevation? Is it given to you? The answer is no. Should they give it to you? The answer is again no, they don't have to give it to you because they have told that in a horizontal ground. And in a single photograph, 2 towers are appearing. So single tower na, that means height of the tower is what? Constant. In a single photograph na, both towers are coming, which means, right, the flying height is constant for both towers. It's not going to change. Now horizontal ground means what? Elevation remains constant, so that is also constant. So height of the photograph, flying height remains constant, right, and the ground elevation is also remaining constant, which means H minus H1 is a constant for both photographs. The denominator H minus H1 is constant for both photographs, and H minus H1 is calculated as what? It is calculated as R2 H2 divided by D. Correct na? So can I write like this? Can I write like this? H minus H1 is constant for both the photographs. So write R2A of the first photograph into H2A of the first photograph divided by DA of the first photograph should be equal to R2B into H2B divided by DB. Correct na? Absolutely yes. This is common for both the photograph. Equate for the common parameters. Okay. Who is the only unknown here now? H2A is the only unknown. Let us solve it. So what is R2A? 4 centimeter. right, H2A, I need to calculate height of the tower A. What is DA? 1.5 centimeter is equal to, what is R2B? 6 centimeter. What is height of the tower B? 80 meters divided by relief displacement is what? 2 centimeter. Observe, did I change any units here? Did I make everything into centimeter or meter? I did not, because right, units gets cancelled here. Centimeter, centimeter cancel, centimeter, centimeter will cancel, H2 will have the same unit as meters. Yes. So let us try and solve this. So if you solve this, what will happen? This will go 3 times. Yeah. What is the height of the tower H2A? P by 2. This goes 20 times. Okay. This goes 10 times. So H2A is what? 6 into 10 into 1.5. So 1.5 into 10 is 15. 15 into 6 is what? 90 meters. Correct now? Please check the calculation. Okay, this goes 20, this goes 10, 60, 6 into 10 into 1.5. 15 into 10, yeah, you should get it as 90 meters. So the height of the tower B is what? 90 meters. Absolutely good question. Unless and until you know what relief displacement means in the photograph, what is the radial distance R2 means in an actual photograph, you will not be able to find the answer for this. Right, very good question. Okay, yes, conceptually strong question. This is what we can call it as synthesis and analysis. I told you, we have 4 abilities that they will check in gate examination. This is checking that, synthesis and, their analysis part. Yes, some amount of recalling is also there because you need to recall the equations. Yes, very good. Let us move on to the next question. Yeah, so this is a question from our errors and adjustment chapter. As I told you, last year, 23 we had question, 22 had a question, 21 we had question, 20 also we had question. One question is coming from this chapter regularly, very, very important chapter for us. Look at this. The most probable value of 2 angles are 40, 20, 30 plus or minus 2 seconds and 84, 44, 20 plus or minus 3 seconds. Mind my language, I don't say 84 degree, 44 minutes and 20 seconds. For my convenience, I'll say 84, 44, 20 plus or minus 3 seconds. The probable error of the sum of these 2 angles will be dash. Okay, so how do you calculate the probable error? Right, so before that, please remember, they are asking you for the sum, probable error in the sum of the 2 angles. So it is A plus B. Okay, now how do you find out the error in sum? The equation goes something like this. The error in sum, the whole square is equal to dou S by dou A into error in A, the whole square, okay, this square plus dou S by dou B. You can write it at whole square also, no problem. Dou S by dou B, the whole square into error in B, the whole square. That's it. This is how your calculation will be. For whatever condition, whether it is the product of A and B, whether it is the sum of A and B, whether it is A by B, the approach remains the same. Yes. Now look at the partial derivative of the sum with respect to A and tell me what is the value. If you are taking dou S by dou A, B is taken as constant, derivative of a constant is 0, so 1 plus 0 you will get. Similarly, what is dou S by dou B? Dou S by dou B means A is constant, so derivative will be 0, and dou B by dou B is 1, so 0 plus 1. So this is 1, this is also 1, so this is all equal to 1. Okay, so since the derivatives are equal to 1, what happens to my error in sum? The whole square is equal to, right, error in A, the whole square plus probable error in B, the whole square, or the probable error in sum is equal to plus or minus under root of EA square plus EB square. EA square plus EB square. So what is the probable error in sum is equal to plus or minus under root of, right, 2 square plus 3 square. What is the answer? Plus or minus root 4 plus 9, root 13. Root 13 comes out to be plus or minus 3.6055 seconds. Okay, you can remember it as a standard value. Okay, root 13, 3.605, root 10, 3.1, like that, you can remember certain values. So the answer here should be what? Option D. Now, you can always remember this as a formula also. The error in sum of two or more quantities is always equal to plus or minus under root of EA square plus EB square. One more angle was there means EC square will come. Right? You can remember this as a formula. But provided the coefficients of this particular A plus B plus C are equal to 1. If it was 2A plus B, dou S by dou A would have been 2. If it was A plus 2B, right, dou S by dou B would have been 2. Then the things will change slightly. So mug up the formula if you want, but gate will check these exceptions. Okay, are you really sure about what you are learning? So these areas gate might just investigate a little bit. So remember, this formula is applicable only if the derivatives of all these particular partial derivatives of this particular sums are equal to 1. If there is a coefficient, then the entire discussion will change. Right. So you need to be a little bit better in mathematics. Yes. Next step. Two stations A and B are 72 kilometers apart. The elevation of the station A and B are 372 meters and 480 meters respectively. The intervening ground, okay, in between ground is having a uniform elevation of 328 meters. The height of the signal required at B if the line of sight has to pass at least 3 meters above the ground at all point. Okay, you see, this question is actually from triangulation. This question is actually from triangulation, but it need not be from triangulation. It can be from leveling also. In triangulation, whenever we are discussing the concept, one very important requirement is that your height of the tower or the height of the signal that you are keeping on top of a tower, right, should be such that the line of sight is at least 3 meters above the ground at all point. This is a very, very important condition in our triangulation. There should not be any grazing lines. If grazing lines come, the refraction effects will be too large. You need to avoid it. So how do you solve it? Let us try and understand. It will be a little bit difficult for you to solve it yourself. So please don't write anything, right? Please observe. Okay? If possible, you try and give me some answers. Keep your calculators with you. Okay. So let us try drawing some figures here. So imagine that this is the intervening ground that I'm having, which is having an elevation of 328 meters. What they are saying is, my line of sight should never touch this particular point. The line of sight should never touch this particular point. How the line of sight should be? It should be a minimum of 3 meters above the ground at all point. So if 3 meter distance you need to maintain, what will be your new elevation of the reference surface? What is the new elevation of your reference surface? 328 plus 3, the new elevation of the reference surface should be what? 331 meters. So the point is, the line of sight can touch 331, it can be tangential to 331, but never below it. That is the idea. Now, there are 2 points here, A and B, they are saying. So let us assume this is where A is, and somewhere around here, let us assume that we should have the point B. What is the elevation of A? You see, the elevation of station A is 372. From A, I am looking at B. So they want the signal at B. So from A, I need to look at B. While standing at A, my elevation is what? 372. So tell me, is 372 above 331 or below 331? No doubt it is above 331. So this is where my point A is. Okay. So somewhere around here, let us assume that we are having point A, which is having an elevation of 372 meters. Which is having an elevation of 372 meters. Now you should tell me, as an observer standing at A, what is the height of my line of sight at A above the 331 meter level? Now your reference surface is 331, so every height that you have will be measured from that 331 only. So 331 is your reference elevation, 372 is your actual elevation, then what is the height of line of sight above the reference? 372 minus 331. You should get the answer as how much? 41 meters. You should get the answer as 41 meters. Right. So please understand. You are having a height of 41 meters. Your line of sight is having a height of 41 meters above the reference surface. Now, standing at this particular point, what you are going to do? You are going to look towards your horizon, and your line of sight will come like this. Right. Your line of sight should come like this. Now tell me, are we grazing this particular point? Yes. So this becomes your new horizon. I can write like this. This becomes your new horizon. This particular point up to here becomes your new horizon. See, your line of sight is 3 meters above. We can consider that as the horizon. Now tell me, if HA is the height that you are having above the reference surface, if HA is the height that you are having above the reference surface, right? Can you tell me what is the distance to the visible horizon, right, for the observer A? What will be the distance to the visible horizon for the observer A, dA? This distance to horizon value. We know the formula, dA is equal to what? Under root of HA divided by 0.06735 kilometers, provided the height of the observer's line of sight is given in meters. Can you please tell me the answer for this? Okay, let me just try it, okay? So I'm getting it as how much? 24.673. I'll take it as 67 kilometers. Okay. So the distance to the visible horizon from A is 24.67 kilometers. Now, if so, what is the distance to the visible horizon up to the point B? What should be the distance to the visible horizon up to the point B? Can you imagine what this value will be? You can easily find out that value because what they are saying is, right, the total distance between A and B. What is that? Total distance between A and B is 72 kilometers. So the total distance between A and B is 72 kilometers, and if dA is 24.67, what is dB? It will be nothing but 72 minus dA. Correct now? Yes. Let us go ahead and find that. So what is dB? Distance to the horizon for the observer standing at B will be 72 minus 24.67. Right. So what will be that value? 0.335, 25.5 plus 2, 7, 30, 47.33 kilometers. I'll get the answer as how much? 47.33 kilometers. That is the distance to the visible horizon for the observer standing at B. Now, whatever we did, we do reverse. We had HA, from HA we find out dA. Now we have dB, from dB you find out what? HB. What is HB? Height of line of sight required. Height of line of sight required above the 331 meter reference. Above 331, that is your reference surface now. So above 331, what is the height at B that you require? What is the height at B required? So tell me, what is the height at B required above the 331 meter level? It will be 0.06735 into dB square. Let us substitute that value here. So, yeah, so .06735 into 47.33 whole square. So I'm getting the answer as 150.87 meters. So you see, as an observer standing here, right, what is the height of line of sight I require above the 331 meter level? Right, above the 331 meter level, the height I require at B is what? 150.87 meters. Right. So from here, I need 150.87 meter to find the reduced level of the point B. So tell me, what will be the required RL of B? What will be the required RL of B? Therefore, the required reduced level of B should be equal to what? 331, correct na? Plus 150.87, plus 150.87. 331 plus 150.87, what is that? 481.87 meters. Right. So the required reduced level of this point is what? 481. Okay, sorry. Should be 481.87 meters. That is the required reduced level of B. So this much I require, then only my line of sight is 3 meters above the ground at all point. That is the minimum required value I have. But what is the actual reduced level of B? That is only 418. So unfortunately here the problem is my point B is only having an elevation of how much? 480. Okay, so this is where my point B is, and what is the elevation of point B? 418 meters. So you see the problem. I need 481, but I only have 418. So how do I solve this problem? Very simple. I'll solve this problem by putting a tower here like this. By solving the problem, I'll put a tower here like this so that my signal at B can reach this level. Then what should be the height of the tower? Top reduced level is 481, bottom reduced level is 418. Then what is the height of my tower? 481.87 minus 418. What is the answer? So, yeah, 63.87. I'm getting the answer as 63.87 meters. Okay, that is my answer, 63.87. So the height of the tower at B should be 63.87 meters. Okay, so I hope you are able to understand this question. Anyway, what I will do is I'll repeat the question. Okay, what I'll do is, let me just go and repeat this question. So what they are saying is, right, at the point A, I'm having an elevation of 372. At the point B, I'm having an elevation of 418 meters. Okay, right. Now, the distance between the two towers, they are saying is 72 kilometers. Right. Now, if the observer's line of sight should be at least 3 meters above my ground at all point, what is the height of the tower required at the point B? Right. So, first of all, what should be your reference surface? Your reference surface is not 328. You need to add 3 meters to it because line of sight should never touch it. It should be 3 meters above. So now your reference surface is 331. Observer standing at A is having an elevation of 372. With respect to 331, what is the height of line of sight is having? It's nothing but 372 minus 331. That value is equal to 41 meters. So if you are having a height of 41 meters, what is the distance to the horizon? Can you calculate? Yes, that is coming as 24.67. They are saying total distance is 72, right? This distance from A is 24.67. Then what is the remaining distance towards B? 72 minus 24.67, you will get it as 47.33. Once you have that value, you recalculate what should be the height of the line of sight at B above the 331 meter level. The height of line of sight above B, above 331 meter level is 150.87. I did the calculation like this. We can do that. If the horizon distance is known, then height of line of sight above the reference can also be known. We get it as 150.87, right? So 331 is the reference. Above that you need 150.87, which means the required reduced level of B is 41.87 meters. But what is the actual reduced level of B? 418. I need this much, but I only have this. For the remaining height, I need to build a tower. So the height of the tower is 481 minus 418. I'll get it as 63.87. Very good question. Again, it is checking the ability of synthesis and analysis, okay, that we discussed yesterday. Okay, you need to understand what is happening, apply yourself, and use a little bit of recall to remember the equations. That's it. Okay, very good question. This can be even considered from leveling, but the 3 meter minimum height above the ground is a concept from triangulation. Let us move on to the next question. Sorry. Which of the following are correct? Analytic lens or special convex lenses are used on internal focusing telescope. That particular statement is actually wrong. It is not used in internal focusing telescope. It is used only in external focusing telescopes to make it analytic. Stator diaphragm consists of 2 additional horizontal crosshairs. Yes. See, every crosshair looks like this. One vertical will be there, one horizontal will be there. To make it stadia, we need to provide 2 more additional horizontal hairs. 2 more additional horizontal hairs on the vertical hair. Right. So that statement is true. Tangential method of tachometry is a non-stadia method. Yes. You don't require the stadia diaphragm in tangential method. Just need to have a basic theodolite, 2 vertical angles you need to observe. Your work is done. Multiplying constant and additive constants are unitless. This statement is wrong. Multiplying constant is K, which is calculated as F by I. As this is a ratio, there is no unit. As this is a ratio, there is no unit. Additive constant C is equal to what? F plus D, where F is the focal length in some centimeter, D is the distance of the lens from the vertical axis, which is also within some centimeter range. So centimeter per centimeter means you will get the answer in centimeter only. But you will not express it as centimeter, you will always express that in meter. For example, you will get the value as 25, you imagine, you got the sum as 25 centimeter, but you report it as 0.25 meters. So does the C have unit? Yes. It is a sum of two distances, so it will have distance unit. K is the ratio of two values, so therefore there is no unit there. So that statement is wrong. So the only correct statements will be option B and option C. Yes. The staff reading of 1.5 meter, 2 meter and 2.5 meter were observed on a vertically held staff through a tachometer fitted with analytic lens with horizontal line of sight. If the tachometer was placed 1.5 meters above a benchmark of reduced level 150 meters, the gradient of the line joining the instrument and the staff station is dash. Okay. So, alright, what is the staff intercept here? Staff intercept is nothing but difference between the two staff reading, 2.5 minus 1.5. 2.5 minus 1.5, you get the answer as what? 1 meter. The staff intercept is 1 meter. Vertically held staff through a tachometer fitted with analytic lens. Analytic lens means what? K is equal to 100 and C constant, additive constant is 0. Line of sight is horizontal. So the distance formula becomes K into S plus C. So what is my distance D? Distance D will be what? K is 100 into 1 plus 0. So the distance is what? 100 meters. The distance is 100 meters. Okay. Next step. If the tachometer was placed 1.5 meters above benchmark of reduced level 150 meter, the gradient of the line joining the instrument and the staff is dash. So here, yeah, we will draw a small figure also. Okay. So this is my tachometer here. Okay. So we are having horizontal line of sight to my staff intercept. So these values they are giving. Okay. So the reading at the top is 2.5 meter. The reading at the center is what? 2 meter. The reading at the bottom is what? 1.5 meters. The reduced level of this point is what? 150 meter. It's very, very close. And this reading is what? Backside reading is 1.5 meters. Then what is the RL of this station? What is the RL of this station? Let us call it as Q. We can see it is 150 plus 1.5 minus 2. 150 plus 1.5 minus 2. Correct now, 150 plus 1.5 minus 2. That should be our reduced level of Q. So what is the RL of Q? So the RL of Q is 150 plus 1.5 minus 2. So the answer should be what? Minus 0.5. So 149.5 meters. 149.5 meters. So finally, they are asking us for a gradient. Right. So what is the gradient? Gradient is nothing but equal to delta H by difference in elevation divided by the distance L here. So what is the delta H here? So this is 149, this is 150. So what is delta H? Delta H is nothing but 150 minus 149.5 divided by horizontal distance is what? 100 meters. So this will be turning out as how much? Right? 0.5 by 100. So 0.5 by 100 is nothing but what? 1 upon 200. 0.5 is nothing but 1 by 2, 1 by 2 by 100. The gradient of the ground should be 1 in 200. So the answer should be option A. The best answer is option A. Okay. So just by using some figures, we are able to get the difference in elevation. I need not draw any, equations here. I need not write any equations here. Yes. A circular curve of 600 meter radius and a deflection angle of 60 degree will have mid-ordinate to tangent length ratios dash. So mid-ordinate is what? O0. Okay. Mid-ordinate is what? O0. Tangent length is what? T1i. Mid-ordinate is what formula? 2r sine delta by 2. What is tangent length R? R tan delta by 2. Okay. So if I solve this, R will get cancelled. 2 times sine theta by sine by cos, it will come as cos delta by 2. 1 by cos delta by 2, 1 by cos delta by 2, it comes as 2 times cos delta by 2. So 2 into cos 60 degree by 2. Okay. So tell me the answer for this. Okay. So Let us look at the comments here. Which app? App not opening means what? YouTube, huh? For mechanical, this is civil class. Why you are standing in mechanical? Acha, okay, I understand. Okay. See, first of all, my dear friend, this is not the place to come and talk about it. I understand your anxiety. You don't worry. We will try and update it. Okay. Don't worry. I'll send this information out. Okay. Right. So I hope you are able to solve it. You just find the answer here. Okay. Yes. Next, the distance from the vertical point of intersection to the vertical point of curvature, right, if the length of the vertical curve is 250 meter. So here one important concept we need to know, right. So if we take the our vertical curve here, this is one rising gradient and this is one falling gradient, right, and if I put my vertical curve in between this, if I put my vertical curve in between this, it looks something like this. Let me draw that again. Right. Now, what is the length of the vertical curve? When we use the formula G1 minus G2 divided by R percentage, what is the length of the vertical curve? Please remember, length of the vertical curve is nothing but the length of the projection of the curve on a horizontal plane. This is a very, very important assumption here. Right, in between the gradients of say plus G1 percentage and minus G2 percentage, if I put a vertical curve, the vertical curve length is not actually the curved length, but what this will give you is the length of the projection of the curve onto the horizontal plane. It gives you the length of the projection of the curve onto the horizontal plane. And secondly, this point is known as vertical point of intersection. This is known as vertical point of tangency. This is known as vertical point of curvature. From where the curve starts, this is the intersection of the two gradients. This is where the curve will go and meet the tangent tangentially. And always remember, it is assumed that the vertical curve is symmetrical about the vertical point of intersection, which means this length is L by 2 and which means this length is also equal to L by 2. Please understand, it will never appear symmetrical to you, but it is assumed that it is always vertical. These 2 points you remember. Length of the curve is length on the projection in the horizontal plane. It's always symmetrical about vertical point of intersection. Now let us go back to the question. If the length of the curve is 250 meter, what is the distance from the vertical point of intersection to the vertical point of curvature? Vertical point of intersection to vertical point of curvature. They are asking you for this distance. They should, they are asking you this particular distance here. So what is that particular distance? That distance is L by 2, which is nothing but 250 divided by 2. The answer should be 125 meters. Answer should be what? 125 meters, option C. Please remember that, okay? Right, so that's our answer here. Right, so one point that we should add is it should be measured along horizontal, because distance means can be either vertical distance or horizontal distance. But since they are giving you the length of the vertical curve, we can rule out that vertical distance calculation. We can only discuss about the horizontal distance calculation. So the answer should be 125 based on a previous year GATE question actually. Right, so these two assumptions are important. I wanted to highlight that. Please look at this. Consider the following statements and identify the correct statements. If a weighted quantity is divided by a factor k, the resulting quantity will be having a weight k square times the original weight. Right. So if A is having a weight of WA, and if you multiply a weighted quantity with a factor k, is divided with a it is divided, na? They are saying divided. So if A is divided by a factor of k, right? If A is divided by a factor k, what does the rule says? The resulting weight will be original weight into square of the factor. Is that true? We'll have k square times the original weight. That statement is true. The weight of sum of two weighted quantities having equal weight is equal to half of the individual weight. The weight of sum of two weighted quantities having equal weight. Okay. So when there are two quantities, say A, which is having a weight of WA, and B, which is having a weight of WB, right, WB, and if we talk about A plus B is equal to S, what is the weight of S? The rule says that the weight of the algebraic sum of these two weighted quantities is equal to reciprocal of sum of reciprocals of individual weights is equal to reciprocals of individual weights. Now, if both weights are equal to W, what happens? Right, the answer would be, right, this will be 1 by 2W, so it will be W by 2. So it will be half of the original weight. So this is what the rule says. A is having a weight of WA, B is having a weight of WB. If S is A plus B, weight of the resulting S is equal to 1 by reciprocal of weight of A plus reciprocal of weight of B. But if both the weights are equal, what happens? 1 by 2 by W will get, which is nothing but W by 2. So the answer is, it will be the half of the individual weight. That statement is also true. Very good. Corrections applied to observations are inversely proportional to the square of probable error. Corrections applied are inversely proportional to square of probable error. That is wrong. Corrections applied are directly proportional to square of the probable error. This is the rules regarding our adjustment. Weight of an observation is inversely proportional to the square of standard deviation. Weight is inversely proportional to square of standard deviation. Let us try and understand that. So so you observe weight of an equation. What is the relationship between weight and correction? If the weights are unequal, right, the corrections are inversely proportional. Higher weight, more trustworthy, less correction. Lesser weight, less trustworthy, more correction. So they are inversely proportional. What is the relationship between correction and probable error? We just discussed, they are directly proportional. Corrections are directly proportional to the square of probable errors. And what is probable error for a single observation? Plus or minus 0.6745 sigma. So probable error is directly proportional to sigma, then probable error is directly proportional to sigma square, which means weight is directly proportional to the standard deviation square. Right. Weight of an observation is, not directly, inversely proportional to square of standard deviation. That is true. You can go mathematically like what we have done, but if you want to use logic, you can always use logic. Standard deviation is a measure of error, how much you are deviating from the central value which is having 0 error. Okay, so more the value of sigma, more the value of standard deviation sigma, more will be the spread of the curve, less will be the reliability, less trustworthy it will be. Now what is weight? Weight is a measure of trustworthiness. So if a quantity is having high weight, high trustworthiness will be there, the spread of the curve will be less, standard deviation should be more. So what is the relation? Inversely related. That logic if you can use, you can find the answer here. Yes. Right, next step. The scale of a vertical photograph is fixed as 1 in 20,000 with a camera having a focal length of 250 mm. If the contour maps suggest that there is a 300-meter contour line passing through the area, what should be the elevation at which the photograph should be taken? So they are asking you for the flying height of the aircraft. I'll not solve this, I'll give you the equation. The scale is nothing but f divided by h minus h. Now what is the scale? 1 in 20,000. Okay. What is the focal length of the camera used? 250 mm, which I can write it as 0.25 meter. The flying height is not given. And what is the ground elevation? It is given by a contour line of 300 meters. So take this as 300. You can find the answer here. Okay. Yes. Next up, an extensive survey of the area in and around a city for fixing reference monuments, locating and improving property lines and determining their configuration and features of the land is referred to as what? Right, it's referred to as land survey, city survey, topographic engineering survey. The correct answer is city surveys. Right, in an area around a city, they are clearly mentioning it. See, land surveys are mostly cadastral surveys that is used for fixing the property lines. Topographic survey will represent the general topological features of the area like hills, mountains, etc. Engineering surveys are used for data collection. Okay, but here they are planning out a city, therefore I can call it as a city survey. Right, error due to bad ranging is. Please understand, right, the different cumulative errors in surveying are error due to standardization. That means the chain is not of standard length. Next, error due to temperature. Okay, error due to pull. Now, these particular errors are cumulative and they may be positive or negative. Right, chain may be either too long or too short. Temperature in the field may be less than the temperature of standardization or more than the temperature of standardization. Right? Error due to pull. The pull that you apply is either less than the standard pull or more than the standard pull. So these errors are cumulative and they can be either positive or negative. But please remember, the error due to bad ranging. Error due to bad ranging is what? It is cumulative, and the error is always positive. Error is always positive. Correction is always negative, but the error is always positive. Why? Because you imagine you needed to measure the length of the line as, say, PQ. You needed to measure it as D1 plus D2. But due to a bad ranging, right, you establish the point R here. Instead of getting the point R on the survey line, you got the point R somewhere around here. We call it as R dash. Okay. Due to which, what will be the measured length of the line? Measured length is L1 plus L2. Now tell me who is greater. Measured length L1 plus L2, is it greater, or the correct length D1 plus D2 is greater? Tell me who is greater. L1 plus L2 is more, or D1 plus D2 is more? Clearly L1 plus L2 is more. Which means the measured length of the line has increased because of your bad ranging. Your point R is not in the survey line, slightly away from the survey line. So you will measure it as L1 plus L2 instead of D1 plus D2. Measured length increases, which means the error is positive. Correction is always negative. So the error due to bad ranging is what? It is cumulative and positive. Cumulative and positive. Okay? Yes. Right. Next, this is another question. All right. So during chain along a straight line with 20-meter chain, the leader of the party has 4 arrows. So leader has how many arrows? Leader is having the leader is having 4 arrows, and while the follower is having 6. Right. You see, as per Indian practice, we provide 10 arrows. Right. As per Indian practice, we will provide 10 arrows for the leader. The leader will keep 1 arrow. Follower will follow him, take it at the end of the chain length. Again he goes, right, take it again from the end of the chain length. So if he has taken 2 arrows in his hands, it means he has completed 2 chain length. Right now my follower is having how many? Follower is having 6 in his hands. So how many chain lengths have completed? 6. So that is another use of arrows. Rather than representing the end of the chain, it will also represent how many chain length have completed. The number of arrows in the hands of the follower represent how many chain length you have completed. Okay? Yes. Okay, so now this was a previous year gate question. It's a gate 15 question. So actually not gate 15, actually gate 19 question. You please go and try it yourself. This question is exactly similar to the previous year question, the previous question that we did on tachometry. You remember calculation of gradient. So there we calculated distance as well as gradient. But here they are only asking for the reduced level of the station. If you draw the same figure as I have drawn there, you will get the answer here. Okay, no need for any equation, please draw. Right, you can see the similar question in your previous year gate booklet. Okay, so thank you guys. So that's the discussion regarding some concepts from which gate has not asked so far. Right, thank you, and all the very best.